Hello again. I would like to continue the discussion of magnetism, which we started in the talk of Robin Hilgers this morning. Essentially would like to continue at the point where he stopped. And the first thing we should look at is the difference of collinear and non-collinear magnetism. You have seen that there are, of course, different magnetic states. There is a ferromagnetic state and there's an antiferromagnetic state. But there are many more possible combinations of magnetic moments. And in particular, you can also have situations in which the moments at different atoms are no longer parallel or antiparallel. A very famous example in which such a more complex ordering will arise is a frustrated antiferromagnet, as it can occur, for example, on a 1-1-1 surface where you have such a triangular lattice. And if you now would have an antiferromagnetic coupling between adjacent atoms, you can see that you can fulfill this antiferromagnetic alignment for two of these atoms here. So these could be antiferromagnetic, but then the third already, it would be unclear in which direction the magnetization should point. And therefore, in such situations, you very often end up having very complex magnetic systems with very complex ordering. For example, something like shown here, in which the atoms, the magnetic moments of the atoms point in very different directions. Of course, also you can have non-collinear structures which arise due, for example, to the domain walls, where you in principle have a ferromagnet, but you have different domains, one pointing up here and one pointing down here, and then of course the magnetization rotates in between. And these kind of complex magnetic structures are also something we frequently investigate using FLEUR. Okay, if you now step back a little bit and think about how we treat magnetism in DFT in general, what happens, of course, is that our Coulomb equation, written here in a very, very simple form, becomes somehow spin dependent. And that means, first of all, that the wave function now consists of a two-component spinar with a spin-up and a spin-down component, right? And as a consequence, the Hamiltonian becomes a 2x2 matrix in spin space, where the kinetic energy here is, of course, a diagonal in spin, but the potential here can have off-diagonal parts. And of course, then we still have the density as a square of the wave function, as usual, and the magnetization of the system defined in terms of the vector of Pauli matrices. When you have, of course, collinear magnetism, the magnetic moment always points in one direction. So you have a single direction, which we usually call the Z direction. And then the Hamiltonian becomes spin diagonal again, because then these off-diagonal terms here vanish, right? And then, since it's diagonal, you can separate this equation here into separate Coulomb equations for the spin up and one for the spin down. And that is, of course, also computationally advantageous to have such a separation. So if you look at the eigenvalue problem in the collinear case, you have these two separate equations here, while in the non-collinear case, since the potential has these off-diagonal terms, you have one big equation here. And since this diagonalization scales roughly cubical with the size of the matrix, it's of course much easier to do two small matrices than one big matrix in your diagonalization problem. Also, non-collinear magnetism usually affects the symmetry, while a collinear system might be still real and symmetric. A non-collinear system is always complex Hermitian, because these off-diagonal terms here are usually complex. Also, the unit cell usually can be larger in a collinear system. I mean, usually you have a small unit cell in the non-magnetic system, a larger one in the collinear, and also a larger one in the non-collinear system. And vice versa, of course, the number of K points, so the irreducible Brion zone behaves the opposite. A very special case of a non-collinear structure is a so-called spin spiral. And that is something which is a very important concept and very often studied. A spin spiral is a state in which the magnetization of magnetization direction of an atom rotates by some fixed angle when you go from one unit cell to another. So essentially what you have is you have some rotation angle here, which is given by some q vector times the position of the atoms. Right? So what then happens is, depending on how the rotation actually exactly works, you can have such a cone here, or you can have such a flat spiral as shown here. Spin spirals are very important and very useful because you can use a generalized Bloch theorem. If you don't have spin-orbit coupling, you can generalize the usual Bloch theorem, in which you have just a translation, right? At the usual Bloch theorem, you have a translation, so the system is independent when you translate it by a unit cell or multiple unit cell, while in this case here, the system does not change when you translate it and also spin rotated by this angle, right? So you have a combined operation of a translation and spin rotation. So while in the usual Bloch theorem, you can say if you apply this translation operator to the wave function, you get the same up to a phase factor, which is then includes this Bloch vector here. Something very similar holds in the case of a spin spiral with this additional spin rotation included in here. And that, of course, also has the effect that you then have Bloch functions in the case of the usual Bloch theorem, or these kind of generalized functions with an additional spin rotation here. The big advantage of this is that you can use now, similar like in the Bloch theorem, where you can simulate a full crystal with just looking at a single unit cell, you now can simulate the full spiral also with calculating only the single unit cell. So you can have small unit cells for large magnetic structures. A very important concept in all of these magnetic structures is usually the concept of the magnetic moment of a single atom, or the local magnetic moment. And for example, I mean, I showed you here some structure where you have such a Neal structure, which can occur in this frustrated antiferromagnet, which we discussed at the very beginning. And there we very often assign essentially a magnetization to a single atom. When you now, of course, look at the magnetization density of the system, you will realize, of course, that this is an approximation and that the magnetization density of the system changes smoothly from one atom position to another, right? So here we have the magnetization roughly in this direction, and then you can see these arrows changing, and then you have a magnetization direction in this direction. However, what you can also see is that very often in some sphere around the core, so in our case, within our muffin tin spheres, the magnetization direction is actually more or less collinear, right? So most of the non-collinear structure is because of these different alignments of these different atoms and in the interstitial. And this, of course, leads to an approximation, which we very often use, in which we constrain the local moments to be collinear within the sphere. And we only have then these different quantization axes of different atoms, which gives a non-collinearity of the system. And, of course, the interstitial region in which we treat the full magnetization density. And that's the default approximation we do in FLEUR. It has quite a few advantages. It reduces the number of the degrees of freedom of the system significantly, gives a clearer physical interpretation, and of course makes more efficient calculations, which also usually converge much better because of these lesser degree of freedoms here. when you do such a calculation, such a non-collinear magnetization calculation, you also very often consider really this direction of the magnetic moment. So on the one hand, of course, we have an input magnetization. As just said, we sometimes, or more by default, constrain this to be collinear in the sphere. And then we have an output magnetization, which might have a different direction. So it might be slightly tilted. There's an angle between the input and the output magnetization in a self-consistency iteration. Then, of course, you have different choices what to do. You might simply neglect the rotation and kind of constrain, therefore, artificially this. You might rotate the magnetization direction in each sphere, or you might also constrain the direction by adding a B field to ensure that actually the input and the output magnetization are collinear. When you want to relax the direction of the local magnetization, of course, in principle, you could say if we don't do this approximation that the magnetization has to be collinear within the sphere, this should happen automatically, right? I mean, we don't constrain anything, and the magnetization should point in whichever direction it wants to point. However, you have to be aware of the fact that we also have the LPW basis functions in the code, and I just put here the kind of representation of the basis function in the sphere. And what you see is, of course, we have a global spin direction. That's the global spin frame we're looking at. And then, of course, we have these functions u and u dot, and they are constructed for a local spin Hamiltonian in which we have a local spin according to our local spin quantization axis we choose, and correspondingly there's a spin rotation. So in that sense, of course, the basis set depends on the local direction which we assume, and therefore it will modify the result a bit. And therefore, if you really want to relax the local directions, you have to adjust these directions in each iteration to make sure that this effect is properly treated. I have to warn you a little bit that these are very new and experimental features in the max releases of FLEUR. And while you're very welcome to play with them and try out, you probably will experience some problems still, and you should definitely be in contact with us if you want to do such kind of calculations. The last part of this talk I would like to spend with an aspect which is also very important in studying magnetic systems, and that's the question of how to map DFT results to model Hamiltonians. Of course, as we just discussed, you can calculate the magnetic structure with DFT, and this works great and it's fine, but of course, there are some problems. On the one hand, the phase space of possible structures is usually gigantic, and it can be very difficult to find the correct structure. And also time dependent can be very hard to include. And therefore, what we and also many other people frequently do is to map the DFT results to some model Hamiltonians, and then use these model Hamiltonians to study the system further. And the simplest thing which you could do is kind of Heisenberg-like treatment, where you have a classical Heisenberg model with a spin on the different sides here and some interaction coefficient J in between. And then, of course, it depends here on the distance between them. The J here has a distance dependence, of course. And what you then do with DFT is you calculate these J coefficients here. Very useful in that respect is the fact that the spin spirals are actually solutions of the Heisenberg model. So what you can simply do is you can simply Fourier transform this Hamiltonian which you have there, and then you transform essentially your J of side n and prime to a J of q. And then you get the corresponding model for the in Q space here, and there you can see directly that this has solutions which are just behaving like these spin spirals we just discussed before. And therefore, the spin spirals are very useful. And of course, also the spin spirals include already a lot of structures which you might be very interested in. For example, of course, the ferromagnetic structure is a spin spiral with a Q vector of 0. You can also have some antiferromagnetic structures with corresponding Q vectors where, for example, here, rho-wise, you change the direction of the magnetic moment, or the Neal state, which we have just seen, is also a specific of a spin spiral state. And therefore, the spin spirals cover already a huge variety of structures. So in determining model parameters, there are, of course, now different ideas. And the simplest thing is, of course, you could simply take your Heisenberg model, for example, a Heisenberg model with two J parameters, so nearest and next nearest neighbor coupling. And then you can essentially look at these what in this model the energy difference, for example, between different states would be, and you can map out the energy in the model, and you compare this energy with the energy of your actual DFT calculation, right? Another possibility to do that, and which is very efficient in some cases, but also has to be treated with some care, is you can use a so-called force theorem. What you do there is, since we said we want to compare total energies of the model with the total energies of the DFT calculations, what we need is the change of the total energy of the DFT calculations. And when you do that in kind of perturbation theory, and you look at the very first contribution to this change in energy, you see that this change in energy is essentially the change in the sum of the change of the eigenvalues, or the change of the eigenvalue sum. And this can be calculated very efficiently because no self-consistency would be required. But of course, the perturbation has to be small, so you have to be very careful with these approximations to do it correctly. We have these force theorem modes implemented in FLEUR. Different force theorem modes actually exist for different quantities you might want to calculate. For example, we have something for the magnetocrystalline anisotropy energy, where you will calculate with different magnetization directions and the spin-orbit coupling, and then you can evaluate the magnetocrystalline anisotropy energy. We also have a spin spiral dispersion mode, in which we calculate spin spirals with different Q vectors, and this allows, of course, then to evaluate the spin spiral dispersion very easily, and also to evaluate, for example, these J parameters relatively simply. We also have a slightly different mode, which is the Jabotinsky-Maria interaction mode, in which we calculate contributions of the spin-orbit coupling for spin spirals. We just said that spin spirals only work in the absence of spin-orbit coupling. So what we do is we calculate a spin spiral without spin-orbit coupling, and then calculate the effect of spin-orbit coupling in first-order perturbation theory. So strictly speaking, this is not a force theorem mode. It's a kind of different calculation, but runs in the same framework here. Okay, so just to summarize, I hope that you got an idea of different questions which arise when you treat more complex magnetic structures. And using FLEUR over time, you will hopefully then become an expert in all these things, and you know all these questions of collinear, non-collinear. We haven't talked about the orbital moment, but you will also learn about that. And hopefully you have, you know about the Heisenberg model, non-collinear magnetism, and so on. Okay, thank you very much for your attention.